Hello, I'm now going to explain to you the last part of section 7.2, which deals with the sampling distribution of the difference of two proportions. Before in section 7.2, what we talked about was the sampling distribution of a sample proportion. Well, now we're going to compare, in essence, two distributions. We're going to look at the difference. We're going to subtract them. So before I get into this and do this example, let me try to explain the theory, and then we'll do an example here to try to clarify what is meant by that. So going back to what we talked about earlier in this section, what we did is we had some population. So let's say if our population was some company, this store, let's say they sell office supplies, and they want to know something. They want to know the percent of their customers that are satisfied with the service. And let's just pretend that it's 70%. They don't know that, but it's 70%. Okay? But they're trying to estimate that using a sample. So what they do is they take a sample, let's say, of size 200. They get 200 of their customers, and they find the percent of that sample that is satisfied. And they are going to get what is known as a p-hat. And so the p-hat is probably going to be somewhere around 0.7, but it's going to vary from 0.7 just because of sampling variability. Maybe it's like 0.68 or something like that. And if they were to take another sample of size 200 and get another p-hat, it would also vary, and let's say in that one it's like 0.72. And of course, all of this is explained earlier in section 7.2, but what a sampling distribution is, it's every value p-hat could possibly take in repeated sampling. Because whenever you get a sample statistic, like a p-hat, you're always saying to yourself, wait a second, this is just one of many I could have gotten, and the actual true population parameter is almost certainly going to be different from this. So a sampling distribution is every value p-hat could possibly take. And all this collection of p-hats, this sampling distribution, will be approximately normal as long as our little rule for that, n times p and n times 1 minus p are greater than 10. And so in this case, that's going to be 200 times 0.7, which is 140. So it'll be 200 times 0.7, and that's 140. And this would be 200 times 0.3, and so that's 60. And they're both greater than 10. Therefore, normality is met. Of course, we talked about all of this earlier. Normality is met. Talked about all of this earlier. And then we can find the standard deviation of this sample distribution. The standard deviation of these p-hats is going to be equal to, and the little formula for that, it's going to be RP, 0.7, times 1 minus p, which is 0.3, over 200. And so if you do that, you would get that it's 0.032404 approximately. And so that's our standard deviation, and so that would be our sampling distribution. But what we're going to do now is we're going to say we have two populations. Let's pretend, for instance, that this is the store that's in Alabama. Let's say the company has two stores, one in Alabama and one Georgia. And so this is the distribution, in essence, of sample proportions of the customers that are satisfied with the service. And let's say they have another company, let's say it's in Georgia. Okay, and let's just pretend the parameter there is 60%. In other words, out of all of their customers, all right, 60% of them are satisfied with the service. If you did a census, and like going back to the Alabama company, let's say our big N, what a big N, that's the whole population size. Let's say that's 10,000. Okay, and it's important that the population size be at least 10 times the sample size. That ensures our formula for our standard deviation work. And so let's say, for instance, in the franchise in Georgia, let's say it has 15,000 customers, and let's just say we take a sample size of 250. Okay, and we're trying to estimate this 0.6. We don't know the 0.6, or they don't know it. All right, but we take a p-hat, and let's say in our sample we get 63% that are satisfied. But the concept of a sampling distribution, it's every value the sample statistic, in this case the p-hat, could take. We're trying to estimate that 0.6. Now, as long as I don't do anything in a biased way, then it'll vary around 0.6 like that, and it's approximately normal because 250 times 0.6 and 250 times 0.4, they're approximately normal. Let's check that. So n times p, 250 times 0.6, and so 250 times 0.6, and so that's 150, and then 250 times 0.4, and so that is going to be 100. All right, they are all greater than or equal to 10. all greater than or equal to 10. All right, so therefore normality is met. Okay, then we can find the standard deviation of this. So the standard deviation of our p hats from Georgia, I'll call this sub G for Georgia and sub A for Alabama. So therefore my P sub A is 0.6 and my P sub G, or it's 0.7, that's 0.6. All right, and so our little formula for that would be the square root of, and that's going to be 0.6 times 0.4 over 250, and that in fact is equal to about 0.03098. Okay, so what we're doing now is we've got two different populations. We want to talk about the difference in the samples. If we were to take a sample from Alabama, a p hat from Alabama, all right, and again find a proportion of that sample of size 200, and if we were to subtract, let's say, the one from Georgia, we're interested in this difference. And just, we are frequently in the world of stats interested in differences. We want to know if the people that, let's say, took the medicine, are they different from the people that took the placebo? Are the students that went through the computer program, are they different than the ones that didn't do the computer program? Or are the trees that got the fertilizer, are their apples bigger than the trees that did not get the fertilizer? We're frequently comparing two distributions, and so that's kind of where we're headed for with this. So we're interested in how this thing varies. And so the concept of a sampling distribution in regards to this is this. All right, so if we were to take a sample, get one of these p hats here, randomly select one of them, and randomly select one of these from Georgia and subtracted them, now we're expecting this difference to be 0.7 minus 0.6 or 0.1. That's sort of what we're expecting, but we fully understand that, hey, we're not likely to get exactly 0.7 here and exactly 0.6 here. Maybe get 0.71 here and 0.59 there, and so that would be 0.12. And so I'm going to put a little d there for difference, just for shorthand. So our d for difference is that. And so if I were to plot that 0.12 and get that, and then if I were to take another sample here and another sample here, they have to be done independently, all right, and I were to subtract them, maybe this time I get 0.09. And if I were to take another difference, if I were to take one of these p hats and one of these p hats and subtract them, and I continually did that, and so I keep getting all of these differences. This is what a sampling distribution of differences is. Okay, and so that is a sampling distribution of differences. And it will vary approximately normal, and we're going to go through all this, as long as all of these is the same thing, n times p and n times 1 minus b, for both of these are bigger than 10. In other words, all four of these numbers. If one of these was less than 10, we would not have approximate normality. So we will have approximate normality. Then let's talk about the standard deviation. Okay, so we have our two standard deviations here. You remember when we subtracted two distributions in chapter 6, you remember we could subtract the mean, so the mean is 0.1, but we couldn't subtract the standard deviations. What did we do? What we would do is we would have to add the variances and take the square root, just sort of like the Pythagorean theorem. And so what it would be, so what is the variance? It's this thing squared. We'll have to find the variance of this and the variance of this and add them and take the square root. So what we would do is you'd say, well, the variance is that thing squared, so if I square that, it just gets rid of the square root sign. So that's going to be 0.7 times 0.3 over 200, and then I'm going to add it to the variance here, which is that thing squared, which is get rid of the square root sign, 0.6 times 0.4 over 250, okay, and that would be the variance of the differences. And then you could take the square root of that to get the standard deviation, and that is the root of the formula on your formula sheet for what we're talking about today, which is right there. So that would, for a sampling distribution, the standard deviation of the difference in two proportions is that. That's probably the most complicated formula we'll have all year, but it is on your formula sheet, and you just plug in those values. And so then when we have the mean, we have the standard deviation, and we've got a normal curve, and at that point we can find areas of these normal curves using normal CDF. Okay, so that's your little introduction, and I know that may be a bit clouded, but hopefully by doing these problems here, it will make sense. Okay, so when you have the difference in two sample proportions, so what we're going to have here, like we said, is we're going to take a sample proportion, so we put a hat on it, from one population, and then we're going to subtract a sample proportion from another population. We're comparing two populations. We want to know their difference. Okay, we want to estimate their differences. All right, so the first thing to realize is that if we did this again and again, it's going to be approximately normal if these four things are all bigger than 10. N times P and N times 1 minus P for all four. For both populations, all four numbers are greater than 10. All right, the mean, you can just subtract, and there's the formula for the standard deviation, which, like I said, is it is on your formula sheet. So let's look at this. Let's look at this example right here. In a particular city, 75% of graduates, high school graduates, can pass a basic physics test. In the city, 40% of the adults who do not graduate from high school pass the physics test. So those are, in essence, our two parameters that we're estimating. So the proportion, I'll put G for graduates, the proportion of high school graduates that can pass the civics test is 0.75, where if they're not a high school graduate, so I'll call that P sub n for not a high school graduate, and so that's going to be equal to 0.4. Okay? So their difference is 0.35, but we're going to have variability because of the sampling variability in the sampling we're going to do. A random sample, that ensures we don't have bias, of 150 of the high school graduates from the city was taken. So our high school graduate sample size, so I'll put little n sub g for high school graduate, and it's going to be 150. And an independent random sample of 200 of the adults in the city who did not graduate from high school was taken. So our sample size for those that did not graduate high school is 200. Okay, is 200. Let P sub g hat, that's a little hat on there, represent the proportion of adults in high school graduates sample that passed the physics test, and P hat sub n represent the proportion of the adults in the non-graduate sample that pass the civics test. Describe the sampling distribution. So we're asked to describe a distribution. We have to cuss. We have to describe its center, unusual values, shape, and spread. Well, in regards to its center, all right, in regards to its center, we have the mean. The mean of all these differences. The mean of P hat sub g minus P hat sub n. And for that, you can just subtract those two numbers. It is just going to be 0.75 minus 0.4, and that's equal to 0.35. And that little formula is right there. So that is, in essence, that formula. So the mean of our sampling distribution of differences is going to be that. So it's going to be centered around 0.35. All right. In regards to its spread, let's find the standard deviation. So our standard deviation of P hat sub g minus P hat sub n. Okay, and so when you do that, our little formula is this. It'd be the square root of, and then first of all, for the graduates, it's going to be 0.75 times 0.25 over 150, and then plus for the non-graduates, and so that's going to be 0.4 times 1 minus that, which is 0.6, over 200. And so when you do that, as it turns out, you would get 0.049497. So that's our standard deviation. And then in regards to the shape, well, let's see if it's approximately normal. For it to be approximately normal, your n times p's and your n times 1 minus p's have to be bigger than 10. So we would say, okay, 0.75 for this, 0.75 times 150, and when we do that, that's 112.5, and then you go 0.25 times 150, 1 minus 0.75, okay, and so that would be 37.5, and then you would say 0.4 times 200, that would be with this population there, so 0.4 times 200, and that is equal to 80, and then we would say 0.6 times 200, and that is equal to 120. All of those are clearly greater than or equal to 10, thus normality is met. Thus normality is met. And so to describe the distribution, I actually don't have space here to do that, sorry. But what you would do is you'd write a little paragraph and you would just say, well, the sampling distribution is centered with a mean of 0.35 with a standard deviation of that, and then the shape is approximate normal. And by saying approximate normal, that takes care of the unusual values or outliers. So that is, in essence, our sampling distribution, okay? Anyway, if we were to draw that, by the way, it didn't ask us to draw it, but you could be asked to draw it. It'd be approximate normal like that. So that would be the shape, and so the middle of this thing would be 0.35. And if you go up one standard deviation to this inflection point, that would be plus 0.49. So this would be like 0.395, let's say. And if you go down one standard deviation, so that's going to be 0.35 minus 0.0495, and so that would be about 0.3005, and so that, and we labeled as normal, and so that would be, in essence, that is all the possible differences. If we were to take many different samples and we were to continually subtract the proportion of graduates that can pass the civics test and say minus the proportion of non-graduates, do that again and again and again, then then these things, you would get a sampling distribution. Okay, so let's answer here's the big question. What's the probability that a sample proportion of graduates is at least 0.4 greater than? Well, we have the normal curve, so 0.4 greater than. Well, 0.4, there's 0.395, so 0.4 is going to be about right there. And so what's the probability that the difference is going to be greater than 0.4? So the difference again, so here's 0.4. So I need this area. Well, that's our old friend normal CDF, and so we can say normal CDF. And then our shaded region starts at 0.4, and then it goes to infinity, goes fully to the right. So I label that as lower bound, upper bound. The mean is 0.35, so I'll say that the mu of my differences, let's say little d for differences. And so then, my standard deviation of my differences is going to be 0.049497. And so when you enter that into your calculator with normal CDF, in fact, so what the heck, let's do it. And so I would go second distribution and go to normal CDF, and we are going from 0.4 to infinity. As a matter of fact, yeah, I just did this problem, so 0.4 to infinity, 0.35, standard deviation is that. And so then, boom, so 0.1562, so 0.1562, and so that is the probability that if you were to randomly select 150 from the graduates, 200 from the non-graduates, that the different, and you were to subtract those two sample things you got, that you would get 0.4 or more. You're expecting 0.35, but what this number is in essence telling us, that's a pretty big percent. It's certainly bigger than 0.05, okay? And so it's a very plausible thing that could happen, that you would get 40% or more. There's nothing unusual. There's no reason to suspect these numbers were wrong. Whereas if this number had been like, let's say 0.03, that would be statistically significant evidence that one of these numbers were wrong, or maybe you're getting a biased sample. That's it. So thank you for paying attention. I wish you the best in regards to the sampling distribution of the difference in sample proportions.